assuming the worst. That's not good. Hurts my feelings to some extent. So, chapter 3, we're gonna. Chapter 3 will mostly focus on quadratic functions. So we're going to look at quadratic functions, quadratic equations. We're going to see whether we can find, well, you'll see what I'm talking about. So we're going to be focusing on equations. So again, as I just mentioned, I'm going to water down the portion of just complex numbers. We're just going to introduce them, just play with them a little bit. We're not going to dive into all the deeper theories of complex numbers because, well, to be honest, you know, you don't need it. It's just some fun exercises. So, equations. Let's talk about solving. Why is it still equations? So we understand conceptually how to solve equations. Let me give you an example of an equation that makes you happy, right? We already, see, told me you're going to hate it. Does that make you happy? How do you solve that equation? Just add 1. And I might start talking a little crazy right now. So that x equals 1, right? So we're good. And we were wanted, the way we think about this problem, we have this number, -1. So we're thinking about what is called additive inverse of -1. So if a number such that if you add it to -1, becomes 0. That's called an additive inverse. Kills a number by means of addition. So -1 happened to have an additive inverse, which is a positive 1. And we're happy with positive 1. We know that number from, you know, that's the first number that we know, probably, right? That makes, it's a little weird, but you're okay with me talking about that right now, right? Nothing, it's not freaking you out, except for the part that I'm talking about. That's probably what's freaking you out. But the question is not. If I make it a little more interesting, 2x minus 1 equals 0, would you be able to solve that equation? Yeah, because how do you do that? Add 1, so good. We had additive inverse. So 2x equals 1. So now you're thinking about how do you kill the 2? Divide by 2 or multiply by 1/2. So 2, we're looking for multiplicative inverse. So it kills 2, turns it into 1. And so we had to invent a fraction, right? X equals 1/2. And we're still very much happy with whatever just happened here, right? You were very comfortable with x equals 1 and x equals 1/2. Well, now I'm going to change this problem, x minus 1, and I'll make it, I'll take it to a point in history where it would freak people out and make it absolutely impossible to solve without getting very creative. This is a whole different, much harder problem than the original that I wrote. How would you solve this question? Subtract 1. You just thought, okay, 1, do I have additive inverse of 1? Well, that's -1. Well, x equals -1, right? Makes you feel very comfortable, but that required an invention of whole new set of numbers, the negative numbers. Right? And if you think about this, and we kind of talked about different types of real numbers, but negative numbers are pretty much made up. I mean, what is a -1? From, from a real life point of view. That's a made up number solely to solve this little equation. Okay? We're just trying to, solve as many equations as we can, so we're just making up numbers as we go. And we made up negative numbers many, many years ago. So we can solve this little equation. Are you okay with that, though? Yeah. Now, at the same time, if I give you this equation, x squared minus 1 equals 0, do you know how to solve that equation? Add 1, so x squared equals 1. square root both sides. So x equals, which is, what's the square root of 1? 1. But you need to remember to do plus or minus, because there are two numbers that are going to come out of that. And we're still relatively happy with it. We haven't reviewed that yet, but this will happen in chapter 3, the deeper review of how to solve quadratic equations, but we're still happy. Positive 1, negative 1, numbers that we've already invented. We don't have to do anything else. But, again, if I change this problem ever so slightly, something like that, and if I try to follow the same procedure, subtract 1 first, right, and then take the square root, so x equals plus or minus square root of negative 1, right? That's the I thing. So this is from everything we talked about. It's borderline dangerous to take square roots of negative numbers. There is no real number that works here. Because again, remember, when you take the square root, you're looking for a number such that if you square it, you get the radicand. And from what you know, no matter what number you take from a real number line, and you square those numbers, those are going to come out positive. So there is no real number, square of which is negative 1. Are you with me on that? So right now, this is not a real number. But we still solve this equation. That's a pretty little equation. No reason for us to discriminate against x squared plus 1. So just like with the negatives, we have to invent a whole new family of numbers. And this is, some of you know, this is where the I comes in. So we define an imaginary number. It's not a real number. It's made up. Imaginary. But anyway, so that's a little pre-story. So imaginary and complex numbers. So the definition of the imaginary unit, we call it I, and that is defined as the square root of negative 1. So that's the imaginary number I. It's not a real number. It does not live on the real number line. Only real numbers live there. Imaginary numbers live kind of next to it, but not on it. And apart the definition, another property, if you square I, you get negative 1. So I squared equals negative 1. So that will be the definition of the imaginary unit I. Okay? So nothing too scary about that. Just accept it as something that we need to solve equations at this point. Just like some distant relatives of yours accepted the negative 1 as a number that you needed to solve equations. It's kind of the same step forward. Okay? How many of you dealt with imaginary numbers before? Most of you? Okay, good. So we also define a complex number by the following. It's a plus bi, where a and b are real numbers. So we say that a, that's the real part of a complex number. And b is the imaginary part of a complex number. So when you deal with complex numbers, and I'm trying to cut down on that, but when you deal with the complex numbers, you always want to be able to identify its real part and its imaginary part. Because actually knowing the real part and the imaginary part of a complex number is actually it helps us to locate that complex number where, in a place where it lives. Like, you can locate a real number line, you can locate a complex number what that thing is. It's called complex plane, but we're not going to really get into that. Okay, so a few examples. Here's a number 3 minus 2I. That is a complex number. It has a real part, that is 3. So the real part of this number is 3. The imaginary part of this number is whatever comes before I. So it's negative 2. So negative 2 is the imaginary part. Is that okay? So that's example of a complex number. Let me give you another example. How about 1 plus I? Is that a complex number? Can you tell me the real part? 1. Can you tell me imaginary part? 1. Good. So it's 1 and 1. Is that okay? Any questions? What about 5I? Is that a complex number? Why not? Well, so what is the real part then? 0. So it's a complex number. 0 is the real part. So the real part is 0. Imaginary part is 5. So that's a purely imaginary number. But it's still part of the complex number world. So it's a 5 pi. How about 7? Is that a complex number? Why not? Just a real number, but can I still call it a complex number? We know how I can call an integer irrationals too, because it satisfies the definition. Right? Is that a rational number, first of all? Is 7 rational? Yeah, it's 7 over 1, so it satisfies that. Is that complex? Yeah, what's the imaginary part? 0. So complex numbers with 0 imaginary part are real numbers, but it still belongs to that world. So we always like, when we expand our sets of numbers, we always like to include everything we had before. So every real number is still a complex number where the imaginary part is 0. Okay? Don't write this down, but this will kind of help you to understand why we do that. So you understand the real number line, right? The real number line. That's where all the real numbers live. Now the complex numbers, they live on a complex plane. So that's a 2D world. You have real axis and imaginary axis. So a number like 3 minus 2i tells me it's 3 on the real axis and negative 2 on the imaginary axis. So number 3 minus 2i lives here. 1, 2, 3, 1, 2. So this is 3 minus 2i. So it's just a point in a complex plane. So it's a two-dimensional space. The horizontal axis is the real, and the vertical axis is the imaginary. So if you have real numbers, they still belong here. Real numbers like number 4, it's just directly on the real line, but it's still part of the bigger picture. Same way the number, 5i, it's entirely on the imaginary axis, but still part of the bigger picture. Okay? The weird part about complex numbers, it's hard to compare them. It's hard to tell which one is bigger. With real numbers, it's pretty clear, right? How do you say whether one real number bigger than another real number? How can you say that 5 is bigger than 4? How do you define number is bigger than another number? What? Yeah, but how do you know? How do you know that 5 is greater than 4? I mean, how do we know that? Common sense, okay. Well, yeah, that's why I'm asking, because this is a really simple question, but the way we define, the greatness, the size of a number is its distance from the origin. 5 is further than 4 from the origin. So you can actually define that the same concept for the complex numbers. You actually have to figure out the distance of a number from the origin. So that's a distance formula. So it's a square of the real part plus square of the imaginary part under the square root using the distance formula. So this is how you can compare the size of the complex numbers by actually doing the distance from the origin. Yeah. So that was fun. Does that make sense? It all comes down to distance. Whichever has higher distance is a bigger number. But anyways, it's a little sidetrack, so if you didn't get that, that's okay. All right, but arithmetic of numbers. So arithmetic of complex numbers. So addition, subtraction is pretty straightforward. Addition, subtraction it just basically comes down to combining like terms. If you understand how to combine like terms, then you understand how to add complex numbers. Okay, so I'm just going to give you an example. There's nothing to it really. For example, 4 plus 7i, here's one number, plus 3 minus 2i. Can we do that? And this is just forget about I from our perspective, that it's an imaginary number. Just think of it as a variable. If this was x instead of I, you would have absolutely no problem performing this operation. You just drop the parenthesis because of the addition, and then you combine. I dropped the 2, right? And then you combine like terms. 4 plus 3 is 7, 7i minus 2i is 5i. So that's the sum of these two numbers. How's that? The real part is 7. The imaginary part is 5. So that's okay. Same thing goes about subtraction. Subtracting complex numbers. If you understand how to distribute a negative and combine like terms, then you're good. So you're in very good shape. Again, for example, if you have something like 3 minus 2i minus negative 2 plus 3i, we should be able to do that. Just opening up a parenthesis, combining like terms, and so forth. So that's 3 minus 2i plus 2 minus 3i gives you 5 minus 5i. Just combining like terms. Is that okay? All right, good. So the real part is 5. Imaginary part is negative 5. So again, that's important for you to be able to identify the real part and the imaginary part. And the trick is, with the imaginary part, you don't need to include I. That's a common mistake. When I ask what's the imaginary part, you tell me negative 5i, and you put that in my math lab, and I'll mark you wrong. I should not be part of the imaginary part. It's just a constant in front of the I. Is that okay? So that's really easy. Multiplication is also pretty simple. Multiplying complex numbers, it just comes down to distributive property or the FOIL. You just either distribute a number or you FOIL, and that should be pretty straightforward. So it's either distributive property or a fancy distributive property, which is FOIL. So then, again, you just treat I as you treat any other variable. So I times I is I squared. You just have to remember that I squared is something nice. What is I squared? What? Negative 1. Okay. So here's some examples. So if I want to go 7i times 1 minus 3i. So I'm just using the distributive property. I'll have to run 7i through this expression. So 7i times 1 is 7i. And then 7i times negative 3i is negative 21i squared. Just your basic algebraic manipulation, nothing fancy. Question? Right. Yeah. Because again, your final goal is to be able to identify real and imaginary parts, which you can't right now. But yeah, but I squared is negative 1, so it becomes negative 21 times negative 1. So negative for negative give you positive, so you can write it as 21 plus 7i. So the real part is 21, the imaginary part is 7. Is that okay? Questions on that? That's from the I squared. I squared equals negative 1. Right? That's part of the definition. Here's another one. 4 minus 2i times 3 plus 7i. So multiplying two complex numbers like that, so we have to FOIL this thing out. So it's 4 times 3, so that's 12. 4 times 7i, that's 28i. Negative 2i times 3 is negative 6i. And negative 2i times positive 7i is negative 14i squared. Right? And what is I squared? Negative 1, therefore what's going to happen with the negative in front of 14? Can I just make it plus then? I'm going to skip a step. 12, combine like terms, 28 minus 6 is 22i, and negative 14 becomes positive 14. We're okay with that quick flip? The negative became positive because of I squared. Now keep going. 26 plus 22i. So the real part is 26. Imaginary part is 22. How is that? Is that okay? All right. How about this? 3 plus 5i quantity squared. How would we perform that computation? Write it out, FOIL it, or use the formula. The double product, we should be able to use it more frequently. So remember how it goes? It's first squared plus the double product plus the last squared. This is your favorite square of a sum formula. Remember me drawing squares and rectangles and all that fun stuff? Yeah, that's the one. You'll see me use this again today, so it's an important formula. Right? Now simplify. 3 squared is 9 plus 2 times 3 times 5 is 30. So 30i. And then 5i squared. What's going to happen there? Well, 5 gets squared as well, right? So it's negative 25. So it's 5 squared times I squared, which is 25 times negative 1. So it's negative 25. Is that okay? Combine like terms. Negative 16 plus 30i. So negative 16 is the real part. Positive 30 is the imaginary part. How is that? Notice what just happened. We took a complex number and we squared that complex number, and we got another complex number. You with me on that? See that? So just by squaring a complex number, we still got another complex number. Just a very simple observation. You with me on that? Okay. So now let's try to make another simple observation. What if I take 3 plus 5i and I'll multiply it by 3 minus 5i? What should I do here? Well, eventually, yeah, because you can use the difference of squares formula instead of FOILing. We know the difference of squares formula. A plus b minus b equals a squared minus b squared, right? Are you with me on that one? So what happens here? 9 minus negative 25. 3 squared is 9, 5i squared is negative 25. So overall, it's positive 34. Isn't that special? I took a product of two complex numbers, and I got another complex number, but a very special complex number. We call that complex number a real complex number, and a positive real number, period. It's a positive integer. That's quite awesome. Keep that one in mind. Now, what is the pattern? What's so special about this pair of numbers? I mean, are they just totally random, or there's something awesome happening there? What is the pattern between those two numbers? Yeah, the conjugates. They differ by a sign in the middle. That's a fancy term for that. If you have two numbers that are differ by a sign in the middle, we call them conjugates. In this case, if two numbers have the same real parts but opposite imaginary parts, they're called complex conjugates. And every time you multiply complex conjugates, you're going to get yourself a real number in the end. And not just a real number, a positive real number. So in general, the product of two complex conjugates, these are two complex conjugates. If you do the math, you expand it, you do your I squared, you combine like terms, it will always come out to be a squared plus b squared. That's what happens every time you multiply complex conjugates. This is why you never had a formula for the sum of two squares that never factored for you before. You remember that? If your answer was like x squared plus 4, you would say, I cannot factor that. The reason for that, in order for you to factor x squared plus 4, you needed complex numbers. You needed an I in there. So actually, x squared plus 4 factors into x plus 2i and x minus 2i. But that's besides the point. Are you okay with that? All right. So you can actually factor a sum of squares using imaginary numbers. So we understand how to add, subtract, multiply, but we don't know how to divide. So here's an example. I want to divide 2 minus 3i. I'm just going to do one example of division. This is the part that I'm removing from the homeworks or quizzes, but divided by 5 plus 2i. And the division of complex numbers is pretty messy. Because really what I'm writing here is 2 minus 3i over 5 plus 2i. Okay. Now, don't write this down, but if my problem was 2 minus 3i over 7, would we have issues with division here? I mean, is that a hard thing to divide? What is the real part of this number? 2 sevenths. What is the imaginary part? Yeah, negative 3 sevenths, right? So you're dividing both by 7. So 2 over 7 minus 3 over 7i. That's really what's happening. But that's not the case in my example. My denominator is not a pretty positive integer. So, for those of you who are friends with your short-term memory, is there a way to turn a complex number into a positive integer? Is there something I can multiply a complex number by to turn it into a positive integer? Oh, what? What? Anyone remembers? Conjugate. Multiply by the conjugate. I think he's just messing with me. He remembers. So times 5 minus 2i over 5 minus 2i. I'm multiplying by the complex conjugate of the denominator. Because then my denominator turns into an integer. So it's 2 minus 3i, 5 minus 2i over 5 plus 2i, 5 minus 2i. So my denominator is easy now. It's the square of the real part. What is the square of the real part in the denominator? 25 plus the square of the imaginary part. What is the square of the imaginary part? 4 plus 4. So my denominator is 29. A squared plus b squared. In the numerator, I have to go through the motions. I have to FOIL 10 minus 4i minus 15i, and then plus 6i squared. Right? If I do the actual FOIL, am I doing my FOIL correctly? Looks weird. I think it's okay. So let's do this in our heads. I squared is negative 1. That makes 6 negative. Yeah, 6i squared. So this 6 is negative now. So 10 minus 6, that's a 4. And then negative 4 minus 15 is negative 19. Okay? So then my real part is 4/29, and my imaginary part is negative 19/29. So I can clearly state the real and imaginary part. Sometimes you're asked to separate them on your homework, but actually you won't be now. But anyway, so that's the math. Before, I mean, it's pretty random. By looking at this number, there is no way you can just say, well, clearly it's 4/29 and negative 19/29. It's not really, right? It's not a clear numerical pattern that you just can notice. Okay? That's how you divide numbers. I mean, complex numbers. You divide complex numbers by multiplying by a creative one. Because again, remember, the only thing we can do legally is multiply by 1, well, sometimes add 0. That's another legal thing. Is that okay? So anyways, good. Division, not that important. As far as solving equations, we won't need much of a division. But simplifying radicals, that's what we really need. So I'm just going to start you with a whole bunch of examples. The idea there is if you have a square root of a negative number, that is the same as saying the square root of b I. So you can always pull out a negative under the square root, turn into I. Okay? Actually, your book, most of the time, will write I times square root of b, for the reason that if you write it the way I wrote originally, sometimes it feels like I is under the square root, just the way you write things. I is never under the square root. It gets really funky for this. But so this is just notation, no big deal. But if you have a choice, put the I before the square root to avoid the confusion of I being inside the square root. So let me give you a few examples. Square root of negative 4. Okay, can we express that in terms of I? What do you think that will be? 2i, whoever said that. Because you can take the square root of 4, that's a 2. You can take square root of negative, that's an I. So 2I. And I can ask you the square root of negative 25, and you will say 5I. And I can ask you square root of negative 18, and you will say 3 root 2, I somewhere in there. Very good. So this is how your book will probably write it. 3I square root of 2. So just to put the I, you know, in front of the square root. But these are just products, so any order is okay. As far as I'm concerned, when you're going to work on your exams, this is perfectly acceptable as far as the notation goes. Just don't get confused by, you know, what the book says. Okay. And if I ask you what is the square root of negative 29, you will say yeah, square root of 29I, or I square root of 29. 29 is looks very primary, so nothing much you can do. So that's about it. Well, it has to be 29 has to be still under the square root because we haven't done that operation. We took square root of negative 1, that gave us the I, and you know we still have to take square root of 29, so that's the square root of 29. Not much we can do with that. Okay. Um, Your book also dives into examples where you take I and you raise it to some obscure power. And again, it's not that important for our purposes. It's fun to do if I, let's say, ask you to raise I to the power 126. Now, that's a legitimate question. How do you raise I to the power 126? And I'll just show you a little trick. And I'm not going to do it the book way. Because in order for me to do it the book way, I need to talk about this another 20 minutes. Let me ask you this simple question. Is 126 odd or even? Even, right? So that means I can always express 126 as a product, as a multiple of 2. So it's what? 64? No, 63. Is that okay? Now, by the rules of exponents, when do we multiply exponents? Does anybody remember? Because sometimes you have to multiply exponents. In what case we multiply exponents? Would that be the case when you multiply exponents? Sure. So if you have a product, you can always write it in this double exponential form. And what is I squared again? Negative 1. So basically, all I'm trying to do, I'm trying to get negative 1 out of this expression. And now, that's simple. What is negative 1 to an odd power? What is negative 1 to the power of 63? Negative 1. So the answer is negative 1. So 126 raised to the power, what did I say? I meant to say I raised to the power 126 is negative 1. Now, if I take I to any odd power, for example, 213, okay? That's an odd power. Basically, here's what it's going to come down to. If you raise I to an even power, it's either going to be negative 1 or positive 1. If you raise I to an odd power, it's either going to be I or negative I. But let's start slow. Is 213 odd or even? Odd. I don't like odd. I like even because I can work with even in this pattern. So in order for me to make 213 even, I'm going to borrow 1 from it. Is that okay? Is this the same as I to the power 213? I to the power 212 times I? Okay, so I have this little I just hanging on the side, and I'll just do the same operation I did with the above example. 212 is even, so I'll write it as 2 squared to the power 106 times I. Right, I have this extra I just hanging on the side. I squared is negative 1, so this becomes negative 1 to the power 106 times I. What is negative 1 to the power 106? 1. So that's just 1 times I, so that's I. So I to the power 213 is just I. This is kind of silly. That's okay. Good, see? You're enjoying it too. Your book does it kind of differently. There's a cyclical pattern to the powers of I to the power 1 is I to the power 2 is negative 1. I to the power 3, you just multiply I squared and I, you get negative I. And I to the power 4 is I squared squared. So I to the power 4 is 1. So you have this cycle of 4 powers. 1, 2, 3, 4. So what your book teaches you to do is to take your power and divide by 4 and then see what the remainder is. Because 4 goes into 213, who cares how many times, but the remainder is going to be 1. Because 4 goes into 212 evenly. The remainder is 1, so the answer is just I to the power 1. 4 goes into 126, who cares how many times, but the remainder is going to be 2. Because 4 goes into 124, right? So the remainder is 2, so it's same as I squared. I squared is negative 1. Did that make a little sense? I don't. Whichever way. That's not important. Who cares? Whether you can raise I to obscure powers. Yeah? See? Well, let me show you something interesting. You seem very unimpressed with the powers of I. Let me show you a little example. So remember earlier when I was being all silly about solving equations and I was dropping terms like additive inverse and a multiplicative inverse, whatever on earth that meant. Remember that? Say yes? Okay. So in addition to the concept of a multiplicative inverse and additive inverse, we also have a concept of an identity. Additive identity, oh yeah? Okay. And a multiplicative identity. So let me show you this. So additive identity. Let's call it E, for whatever reason, for the lack of better letter. The property of the additive identity is that A plus E equals A. So it doesn't change anything. Okay? In the world that you're living in, what is that additive identity? Does that have the actual value that you can attach to it? 0, right? Adding 0 doesn't change anything. So in our case, 0 is the additive identity. Okay? So at the same time, you have additive inverse. And that means if you take a number and you add its inverse to it, you're going to get that additive identity. So in our case, some number A plus what equals 0. So what do you need to add to a number to get 0? Yeah, negative of that number. Right? So this is our world. This is more abstract world. This is our world. So that means, and you agree that every real number has its additive inverse. You can always put a negative in front of the real number. So this allows us to solve equations. This is going to be on the test because you're not paying attention. I'm going to put this on the test. Okay? So far, October 1st. What? October 1st. Should we around 1-ish? Well, hopefully 1-ish. But additive inverse, multiplicative. Now, same thing works with the multiplicative inverses. Check this out. What? No, it's in class. Pen and paper or whatever you like. So multiplicative identity. The idea there, if you take a number, you multiply by something, it's the same number. So in our universe, well, what is that identity? That if you multiply a number, it's just same number back. 1. So in our world, E equals 1. So 1 is the multiplicative identity. It doesn't change anything. At the same time, the multiplicative inverse is the thing that if I take a number and I multiply it by something, I get that identity back. So in our world, what A needs to be multiplied by to get 1 back? What do you multiply number by to get a 1? 1 over A, right? A times 1 over A equals 1. Works for every real number except for 0. 0 is the only one that does not have a multiplicative inverse for various reasons, right? So the fact that every real number except for 0, because who cares about 0, has a multiplicative inverse allows us to solve equations of the form 2x plus 1 equals 0. You kill 1 with the additive inverse, you kill 2 with the multiplicative inverse. Who's with me on that? Okay. Now tell me, is there a real number such that its multiplicative inverse and its additive inverse are the same? 2. What is the additive inverse of 2? So what do you need to add to 2 to make 0? Negative 2. What is the multiplicative inverse of 2? 1 over 2. So negative 2 and 1 half. Are they the same? No. So the answer is no. 2 does not work. Can you think of another number? Oh, I said real number. You're cheating. Now you cannot think of one? Why not? Give 1. Okay, so what's the additive inverse of 1? Negative 1. What's the multiplicative inverse of 1? 1. Just 1, right? So 1, negative 1. So what you notice that these two numbers have to have opposite signs. In order to make it 0, it has to have opposite sign of the original number. In order to make it 1, it's just a reciprocal. Well, reciprocal retains the sign. So 1 is always positive, 1 is always negative, right? So it doesn't work. There's no real number for which multiplicative inverse is the same as the additive inverse. But you drop I in there, right? Think about I. What is the additive inverse of I? Well, what do you need to add to I to make 0? Negative I, right? I plus negative I equals 0. Right, so negative I is the additive inverse. Right? Okay. What about multiplicative inverse? What do you need to multiply I by to get 1? Well, I times 1 equals I. But I times what will equal 1? Well, that will be negative. But if you follow that reciprocal pattern, that still works. Right? The i's cancel. So I equals 1 equals 1. So 1 over I is the multiplicative inverse. But let's play with 1 over I. If I actually want to divide 1 by I, how do I do that division? How do we divide by a complex number? That other fancy conjugate. And what is the conjugate of I? Negative I. So I'll multiply by negative I over negative I. So that's negative I over negative I squared. Right? Yeah? What is negative I squared? 1, because it's negative of negative 1. So it's negative I over 1 equals negative I. So that means 1 over I equals negative I. Right? One is the multiplicative inverse, the other one is additive inverse. Isn't that cute? This is me trying not to go all kinds of deep into the theory of I numbers. So I just kind of went off on a tangent. And I'll put that sucker on a test. Oh yeah. Okay, good. You want a break? Okay, so quadratic equations. Most of it will be a review. So I'm going to move fast. Okay, a general form of a quadratic equation is something that looks like ax squared plus bx plus c equals 0, provided a is not 0. Because if a is 0, you don't have a quadratic equation, you have a linear equation. So we're going to talk about 4 different ways of solving them, and one is by factoring. It is using the principle that the idea behind solving quadratic equations by factoring is the following. If you have a product that equals 0, the only way two things multiply to 0 is if one of those things equals 0. It's either a equals 0 or b equals 0. It's called the zero factor property or zero product property, whatever you want to call it. Doesn't matter. You can claim common sense on that one. The only way a product is 0 if you multiply by 0. Okay. So example, if you already have something that's friendly and factored, and that something equals 0, then we can simply set each factor to 0 and solve for x. So that should be relatively straightforward. 2x plus 1 equals 0, or x minus 3 equals 0. Solve them separately, 2 linear equations, negative 1/2, x equals 3. And we're done. Is that okay? You kind of knew that before you met me, right? That's not a stretch. If things are not factored, we sometimes can't get them factored. And by the way, I assume your absolute mastery of factoring. You're a master of factors here. Okay? So whatever it is I can throw on the board that is factorable, you should be able to factor it without, much of struggle. Here's a problem. If you want to solve, there's one thing. If you want to solve something by factoring, make sure one side is 0, otherwise it doesn't work. Because again, the product is 0. That's what makes it easier. If the product is 12, well, there are infinitely many options. Infinitely many pair of numbers multiplied to 12. But with 0, it's always easier. Can you factor that? X squared minus 4x minus 12, how do you factor that? Yeah, multiples to the last term, adding to the middle term, x minus 6, x plus 2. So then you set both of those to 0. So x equals 6, x plus 2 equals 0, x equals negative 2. Right? So that's about all I want to show you as far as the factoring goes. If you can factor it, you can solve it. And you should be able to factor it. Even if I put a little constant in front that freaks people out, you should still be able to factor that by your prior experience. Questions on the theory? We're good? Not good? Oh, okay, we're good. All right, so the second type of equations That technique, let's call it extracting the square root. The idea there, if you have something squared equals a number, so you have one big square, whatever's inside the square is irrelevant. It could be other expressions, could be whatever. And the other side is a constant, then x equals plus or minus the square root of that constant. Okay? And again, by x, I mean whatever's squared. Could be some other expression, but as long as it's one big square, we can do that. So this is the idea behind extracting the square root. Don't forget about plus minus. The reason for that is there's absolute value involved, but we don't write it out because it's silly. So just remember plus or minus. And so again, for example, x squared equals 5. You just say, well, follows my pattern. So x equals plus or minus square root of 5. We're done. That's the solution to that equation. Is that okay? What? We're good? How about x squared plus 12 equals 0? How would we go about solving that one? We kind of did that already today. So subtract 12, and then take the square root, plus or minus square root of negative 12. We just learned how to take square root of negative numbers. What would that equal to? I don't need the square anymore there. So just x equals plus or minus square root of 12. What is that equal to? 5? I. Is that it? Is there anything besides I? There's I in there. 2 square root of 3. Okay. 2i square root of 3. The way we do those, 12 is 4 times 3, square root of 4 is 2. 3 stays. Is that okay? Yeah. Again, your book writes it like that, so there's an appearance that I is clearly not under the radical. How about this fun equation? 2x plus 3 squared minus 7 equals 0. Can I still use the same logic? Can I get it to be a one big square equals a constant? Yeah, I can still follow the same pattern. I can add 7 to both sides. I can get it to be 2x plus 3 squared equals 7. Right? And then I can, because again, remember, this idea doesn't have to be just x. It's just something squared. Just blah squared equals a number. So this is what I have. All my variables are inside that square, and the other side is a constant. So I can proceed with this idea to get that. 2x plus 3 equals plus or minus square root of 7. And I can actually solve for x as a linear equation. I can subtract 3 from both sides. So it's 2x equals negative 3 plus or minus the square root of 7. And then divide both sides by 2. X equals negative 3 plus or minus square root of 7 over 2. Is that good? Same idea. Any questions on what just happened? Because it's a little trickier. But again, we're always going to end up with a linear equation, which we like. We like linear equations, and that's what this is. That's really two linear equations. We're just kind of solving them at once. No questions? Oh yeah, it will be the same solution. It'll be a lot harder for me to solve. It's not. It's good if it's like that. If all my variables are inside the square, it makes it easier. Because we haven't even touched when it's all folded out, so it's So it's like that. So you hope it factors, but it won't factor because I mean these are not pretty numbers. Okay. So this is kind of a next step from from the ugliness of this. You can still get pretty numbers out of this. If your example, let's say it's 3 times 4x plus 1 squared equals 12. We can still solve it like that. We have all the variables inside the square. The other side is a constant. Well, I have a lonely 3 up front. Well, can I get rid of that 3? What would I need to do? Yeah. Use the multiplicative inverse of 3. That's what we're doing here. Okay. If you paid attention to that beautiful story. So here we go. Well, now it's a big square equals 4. So take the square root. 2x plus 1 equals, well, square root of 4 is 2, so plus or minus 2. Is that okay? So that's two pretty linear equations. 2x plus 1 equals 2. 2x plus 1 equals negative 2. Oh, because I'm an idiot, that's why. But other than that, it's all good. I just wrote it wrong. You gotta tell me those things. 4, 4, 4. Okay. And then you solve them separately. So in this case, we actually get pretty answers. 4x equals 1, x equals 1/4, 4x equals negative 3, so x equals negative 3/4. So that equation, if I expand it, that will factor into something pretty. If your answers are rational, then your equations are factorable. And it will be we'll make this knowledge official in chapter 4, but it should make a little sense. Because there's a big connection between factoring and actually getting your answers. So if your answers are pretty, then you have pretty factors. If your answers are ugly with square roots, you probably won't be able to factor it into anything that's decent. Was that okay? All right. Well, let's do one more. Feels like we need to do one more. All right, let's do one more. How about 3 times 2x minus 7 squared equals 5? What do you want to do first? Hmm? Yeah, divide by 3, because you don't like that 3. You want your square to be isolated. So it's 2x minus 7 squared equals 5/3. Woo. What do we do now? I mean, it's ugly, but is that conceptually any different? Take the square root. So then it's 2x minus 7 equals plus or minus the square root of 5/3, right? Well, that's all kinds of politically incorrect to write square root of 5/3. Why? What's wrong with writing square root of 5/3? From your previous math courses, I didn't tell you that before, but you should have. Well, it's improper fraction, but there is a bigger issue. The square root in the denominator, kind of, right? You have a square root in the denominator. That's all I'm saying. And this is what you don't want to have that, right? Remember that? Your denominator should always be integers. So we tend to rationalize our denominators because we don't, that's bad to have square roots in the denominators. You know about that? Yeah. How do we fix that? How do you get rid of the square root of 3 in the denominator? Yeah, multiply by radical 3. Very good. So that becomes plus or minus square root of 15 over 3. The reason why we do that, first of all, we like radicals to be, on top. They're the leaders. And And the second reason, it's easier to add fractions. If your fractions are all that ugly, then it's really hard to add fractions. You have to find common denominators when your denominators are irrational numbers. That's weird. So we want to make them pretty. That's why we'll rationalize the denominators. So next step is to add 7 to both sides. So it becomes 2x equals 7 plus or minus the square root of 15 over 3. Right? Technically, we should find the common denominator to make it into 21 plus or minus square root of 15 over 3, but that's not necessary. But we can do that. To see how easy it is to add fractions when the denominators are pretty. It's still on the left, right? It's 2x still equals all that. And then to get x, you divide by 2. So you divide by 2, so 2 will make 3 into 6, so it becomes x equals 21 plus or minus the square root of 15 over 6. I just did the common denominator. I mean, I need it to be, so it's 7 times 3, 3 over 3, so that's your 21. What? I'm skipping a fraction addition step. I should be able to. You can fill that in, right? Okay. Is that good? Yes. Yeah, it's actually, if I open a question, let's say, okay, I need to open a, well, anyways, it's going to be in that little, you have that little column of math symbols, so it will have plus, minus. I mean, if you need it for a problem. Okay. Good? All right. Okay. Third type of equations. Well, let's try this one with the limited skills that we have at the moment. Here's an example. So here's a third type of equations. 2x squared minus 1 equals 3x. So when you have an equation like that, and you're faced with this stage of our development, does that whole extracting the square root applies, what we just did? No? Because we have x squared and then we have a lonely x. We don't have a big square, right? Do you agree with that? Now, really what we have is 2x squared minus 3x minus 1 equals 0. Yeah. So your next hope is to, oh, this is an awful example, but anyways, your next hope, this is probably the worst case scenario of all the problems that you'll see this whole semester. So your next hope is to try and factor that thing. Is that thing factorable? No. Right. Even if you try very hard, you won't be able to factor it. So we're stuck. We don't have another way of doing that, but it would be awfully nice if somehow I can achieve this situation. If I can pack up all my variables inside the square and just have another constant on the side, then we can take the square root plus or minus and solve, right? I don't know yet. Maybe I'll have to. But do you agree that this will be a good development if I were able to go from here to here? Yeah. Now, have we done that before? Have we gone from something like this to something like this? And the answer is yes. You just have to remember when that happened. Completing the square, because we played with circles and we had the random x squares and x, and we pack them into big squares. So we're going to try and complete the square. So now, of course, since we went over that, you remember the idea. Now, here's the idea behind completing the square. when it's coming down to the quadratic equations. First of all, whatever that constant term is, that little constant, I really don't care about that. So I'm going to get rid of that constant, just add 1 to both sides. So that's step 1. Get rid of the constant. So just add it to the other side, subtract to the other side. If it's already on the other side, then good. Now, in your notes, somewhere when I was drawing the squares and looking for the missing corner, remember that? We agreed that in order for me to complete the square, we take the term in the middle, we divide that by 2, and we square that term. Remember that? Take the term in the middle, half it, and square it. We did that very early, 3 weeks ago, something like that. Is that ringing a bell? The reason why we divided by 2 is because of that formula for a square, that 2ab in the middle, so you want to get rid of that too. Okay. You with me on that? Now, the only problem is the examples that we did with circles did not have coefficients. It always started with just x squared. So if you don't have a coefficient, then you're going to take whatever the term next to x, you're going to have it, and you're going to square it. We do have a coefficient, so we need to get rid of the coefficients. Well, how would we kill that too? Divide by 2. Thank God for the multiplicative inverses. Yeah, that's what I'm talking about. So divide both sides by 2. So that becomes x squared minus 3/2 x equals 1/2. That's where we're at right now. So the second step, get rid of the coefficient in front of the square. All right, now we're ready to complete the square. Now, the way we did that before, and the technology there was, do you remember the technology? Let me just write it here. So, completing the square theory. So if you start with something like this, x squared plus or minus, that doesn't matter, plus or minus a constant times x, then in order to complete the square, you will take that constant, you'll divide it by 2, and you'll square it. That's that missing corner when we were shifting squares and rectangles around. Remember that? You thought it was cute? We did that. And by the formula for adding or subtracting the squares, it's going to come out to be the plus or minus d over 2 quantity squared. And this is what you like, because if your whole equation packs inside that, then you can take the square root and you can solve it. Yeah. Yeah, you can. Yeah. Yeah, it will work. But, when you actually solve it directly, just, that doesn't matter. But that 2a, if you think ahead, and you think about quadratic formula, it does have a 2a in the denominator. Right? You know what I'm talking about? Quadratic. Oh, yeah, it will work every time. But because this is what we're doing right now, we're deriving the quadratic formula. That's what happens behind the scenes. Quadratic formula completes the square, really. So complete the square by adding the missing term. So what we're adding here, we have to take 3/2. That's the coefficient in front of x. And we have to half that. So what is half of 3/2? 3/4. So it's 3/4. So actually we're going to add 3/4 squared. Right? That's what we're adding. The half of the term in the middle squared. Right? Is that okay? So if I add something to one side of the equation, I have to add the same thing to the other side of the equation. So that 3/4 squared gets added to both sides. Isn't that fun? No, it's still there. But then it will be gone on the next step. Because then by this idea, it just becomes x minus 3/4 squared. The left-hand side factors into this by that, by that idea. So yeah, technically now 3/2 is gone. It's still part of this expression. If I open it up, the 3/2 will make its appearance again. Now on the other side, it is 1/2 plus, well, 3/4 squared is 9/16. Right? The 3/4 squared 9/16. I need to do the common denominator in order to add 1/2 and 9/16. Yeah, so we have to multiply this by 8 over 8, so that becomes 17 over 16. Right, the common denominator is 16, multiply first fraction by 8 over 8. Is that okay? So now we have completed the square. We have a quantity that is squared equals a constant. So it's back to what we were doing before. I can proceed with extracting the square root. So the fourth step is just extract the square root. So they'll just become x minus 3/4 equals plus or minus the square root of 17/16. And luckily, square root of we have a 16 in the denominator, so it's easy to take the square root. We don't have to worry about rationalizing the denominator in that case. It just happened to come out something pretty. So add 3/4 to both sides. X equals 3 over 4 plus or minus square root of 17 over 4. Same denominator. So I can add them. X equals 3 plus or minus the square root of 17 over 4. So that's my solution. And this is a pretty weird and laborious way of solving this problem. It's called completing the square. Okay. It's an important technique. So we still need to know the process. We'll come back again, as I told you when we dealt with circles. But if you're giving choices to solve a quadratic equation, when it's just like, here's an equation, solve it, probably don't want to do that. This is too complex. Okay? Unless you're specifically told to solve by completing the square, then yeah, solve by completing the square. Try to avoid it. It's messy. But that takes us to the fourth way of solving quadratic equations. Okay? Now you're going to help me. Don't write this down, but help me. I'm going to try and solve this equation. A is not 0. So I'm going to solve this by completing the square. So don't write this down, but tell me what to do. Based on your previous example, assuming you wrote that down. What is the first step in solving equations by completing the square? What is the first thing that we need to do? Subtract c. So the first step was to get rid of the constant. So then we'll get ax squared plus bx equals negative c. Right? What is the next step? Coefficient. Get rid of a. So second step, just divide both sides by a. So we get x squared plus b over ax equals negative c over a, right? Now the third step is to actually complete the square by adding whatever is missing. And the way we do that, we're going to take b over a, and we're going to half it, which will be what? What is half of b over a? You said it earlier. Yeah, it's b over 2a, right? Dividing by 2 just puts 2 in the denominator. So, because, right, it's b over a divided by 2, so it times 1/2, really. That's how you divide by 2. So we're going to add b over 2a squared plus b over 2a squared. That's that missing term. When you take the constant in front of x, you half it and you square it. That's what you get. So, and finally, the left-hand side is just x plus b over 2a squared. So it collapses into that pretty quadratic expression. While the other side, let me play with that a little bit. It's b squared over 4a squared minus c over a. Right? That's my right-hand side. Can I combine those two fractions? I mean, what will be the common denominator between 4a squared and just a? What about 4? Do I need 4 in the common denominator? We need everything, really. So it's 4a squared. That's the common denominator, right? That's the smallest expression that's divisible by both. So we need to multiply this by 4a and that by 4a. So then they have the same denominator. So now this is x plus b over 2a squared equals, I can write it as b squared minus 4ac over 4a squared. Right? For those of you who know the quadratic formula, now it becomes, now it starts looking like something that you remember. Who remembers the quadratic formula? Who want to tell me that thing? Yeah. Are we getting, see, we got b squared minus 4ac in there. Yeah, he's right. So what do I do next? How do I keep solving this by completing the square? What's the next step? Yeah, take the square root, so that's x plus b over 2a equals plus or minus the square root of b squared minus 4ac over 2a. I'm sorry, over 4a squared. I'm jumping a little bit ahead of myself. Now, can I take the square root of that denominator? 4a squared, what's the square root of that? 2a. Now, technically, it's two absolute values of a, but since this whole thing is plus or minus already, then who cares? Right? And then finally subtract b over 2a over b over 2a, negative, plus or minus all that. Same denominator, I can connect them. So that's the quadratic formula. Sure. Well, for whatever reason, if you don't remember quadratic formula, you can either rederive it or just solve all of them by completing the square. Because again, completing the square and the quadratic formula, they're interchangeable approaches of solving quadratic equation. One of them is just a lot faster. That one is. Because all the steps are already built in. Right? You like your quadratic. You know, You guys sing songs to quadratic formula, I've heard, right? Yeah. So let me do a few equations, a few examples using quadratic formula. 3x squared plus 2x equals 7. So in order for me to use a quadratic formula, I need to put it into quadratic equation standard form, get 0 on one end. Now remember then, the idea here is my equation is ax squared plus bx plus c equals 0, and then x is negative b plus or minus the square root of b squared minus 4ac over 2a, right? So for this specific equation, a equals 3, b equals 2, and c equals negative 7, right? These are the coefficients. You just read them in a row. A, B, C. Well, of course, it depending on which term it is. So, negative b plus or minus the square root of b squared minus 4 times a times c. Is that okay? I'm just bringing down the numbers from the equation all over 2a. Yeah? So that becomes negative 2 plus or minus the square root 4 plus what? I don't know, maybe. It's, yeah, 84 over 6. So it's 88 under the radical. So negative 2 plus or minus the square root of 88 over 6. Now, 88 is not a perfect square. So what's the next best thing? Can I simplify that? Two square roots of 22, because 88 is 4 times 22. 88 is 4 times 22. I can take square root of 4, 22, well, nothing pretty. Comes out of 22. So it's negative 2 plus or minus 2 square roots of 22 over 6. Right? Now I can reduce it by 2 because everything is a multiple of 2. 2, 2, and 6 will become 1, 1. No reason to write that 1 and 3. Just divide everything by 2. Right? So that becomes 1, that cancels, and that's a 3. Right? So that's our answer. You don't need that 1. So just negative 1 plus or minus square root of 22 over 3. How many solutions is that? 2. 2 real solutions. Let me do another example. 4x squared plus x plus 1 equals 0. So again, if I want to solve it by quadratic formula, then we get negative 1 plus or minus the square root of 1 squared minus 4 times a, which is 4, times c over 2a. So this is negative 1 plus or minus the square root of negative 15 all over 8. And And we have a negative under the square root. Oh well, we can deal with that now. So it's negative 1 plus or minus I square roots of 15 over 8. And we're done. How many solutions is that? 2. Both complex solutions. No real solution, right? But 2 complex solutions. So let's say I want to solve this one by completing the square. Did I say completing the square? I didn't mean that. I meant quadratic formula. Sorry. Don't worry about it. So negative 20 plus or minus square root 20 squared minus 4 times A times C all over all over 2A. Yeah. Now 20 squared is 400. 4 times 4 times 25 is also 400 over 8. Right? So 400 minus 400 is 0. Square root of 0 is 0. So we're just down to negative 20 over 8, which reduces to negative 5 halves. One real solution, which is fine. Graphically speaking, it's a parabola that's just sitting on the x-axis. It just touches the x-axis once. If you have a quadratic equation that produces 2 real solutions, that's a parabola that crosses the x-axis twice. Those are your 2 solutions. If you have a parabola with just complex solutions, if you have a quadratic equation with just complex solutions, the graph of that equation will not touch the x-axis. If it's an upside-down parabola entirely below, or it's a normal parabola entirely above, so it does not touch the x-axis. Does that make sense? Okay, so there is a way to predict how many real solutions a quadratic equation has, and it's all about what's happening under the radical. If the expression under the square root is positive, then you're going to get 2 real solutions. If the expression under the square root is negative, like here, you're going to have 2 complex solutions, so no real solutions. And if the expression under the square root is 0, you get 1 real solution. So we call that expression under the square root is called discriminant. So D equals B squared minus 4AC. So we can just compute that. You still have to compute that if you solve the equation, but this will give you an idea how many real solutions it has. So we'll just, it will come back a little later. We'll actually use the discriminant. But basically, if D is positive, then we have 2 real solutions. If D is 0, then there is 1 real solution. And if D is negative, then there are no real solutions. You get 2 complex solutions. Okay? So just a little thing, they'll ask you on the homework, compute the discriminant, or just tell me how many solutions it has. You just go quick discriminant. Okay, so it's positive 2 solutions. All right. One last example. Are we ready? A fun one. So I have x plus 2 over 3 squared minus the quantity x plus 2 over 3 minus 12 equals 0. This looks like a pretty messy equation. I mean, I can open up the parentheses, combine like terms, do all that fun stuff. I should be able to solve it. But you might notice that there is a certain pattern in that equation. And the pattern of that equation reminds us of a quadratic equation. You have something squared, then just that same thing, and then a constant. Right? So it follows the pattern of a squared minus b times something, sorry, plus b plus c equals 0. It's the same idea. And we'll see equations like that in many different circumstances where it looks like a quadratic equation, but it's not quite a quadratic. So these are called equations of quadratic type. And the trick, the mathematical trick that we use to solve this equation is first of all realize that it looks like a quadratic, and then forget about all this junk that's inside the parentheses, and then just solve a quadratic equation. So we're just going to replace all that mess inside the parentheses with whatever variable I can think of. We usually like u or w. I'll use u. How does that sound? I'm going to make what we call a substitution. I'm going to say let u equal whatever that thing in the parentheses. I'm introducing an extra variable, a dummy variable, that will make solving this equation a lot easier. So instead of every x plus 2 over 3, x plus 2 over 3, I'm going to put u. So it just becomes u squared minus u minus 4. Okay? So I made my equation a lot simpler. And then I'm just going to solve for u as an intermediate step. Just forget about x, just solve that equation that's in terms of u. That's factorable, right? I can factor that very easily. How would you factor that? I already heard the answer. Yeah, u minus 4, u plus 3, two numbers that multiply to negative 12 and then to negative 1. We set both of those to 0. That's our zero factor property. So u equals 4, u equals negative 3. Right? So that's that intermediate step. I solved for the dummy variable. The equation was in terms of x, so my answer should be in terms of x. So now I'm going to substitute back. And solve for x. Because what is u equal to? What did we agree to let u equal? X plus 2 over 3. And u equals 4. So I can say instead of u equals 4, I can say x plus 2 over 3 equals 4. And I can solve for x. Right? They should be pretty easy to solve for x. Multiply both sides by 3, x plus 2 equals 12. So x equals 10. At the same time, u equals negative 3, so x plus 2 over 3 equals negative 3. So x plus 2 equals negative 9. Is that right? Multiply by 3. So x equals negative 11. So these are my two solutions. It's kind of a sneaky way of solving this. When you notice the quadratic pattern. I didn't have to use it for this problem, but there'll be problems where there's no other way. But to recognize, oh, there is a certain pattern, looks like a quadratic, messy. So forget about the mess, replace the mess with whatever letter you like, solve that quadratic separately, and then go back and plug it into the messy part. So you're splitting it up into a couple easy equations and solving one complex equation at once. Does that make sense? All right, good. So quiz 3 is due. Now, quiz 3 2.0. If you see 2 quizzes 3, do the 2.0 one. If you see 2 homework 5s, do the 2.0 homework 5s. I tried to remove them, but since some of you already started, I cannot really remove them. So that's an alternative assignment. It's not just Jeremy. There are about 4 students who are doing that, so that's all good.